In this video, we are going to talk about mirrors. I'm going to give you some simple tricks that you can always use to deduce or recall the nature of the image formed by mirrors, in particular curved mirrors. This video already is the second part of a first video I did on properties of images formed by lenses. So I'm going to leave the link somewhere here so that you can go and watch it if you want. So a mirror is simply a reflecting surface that forms the image of objects following some laws. In particular, the law of reflection is the main law that comes into play. And this law of reflection itself is derived from Fermat's principle. So Fermat's principle, which tells us that light, if light has to travel between 2 points, let's say A and B, then it's always going to take or follow the path that will require the shortest time to travel between the 2 points. And you should note that this path, the path that requires the shortest time to travel, is not necessarily the shortest geometrical path. So really be careful about this. So from Fermat's principle, we are able to derive the laws of reflection and refraction, which we talked of in the previous video. The law of reflection, it's probably the simplest phenomenon undergone by waves, which means that if you have a light that's incident on a mirror, then the angle of incidence is equal to the angle of reflection. Really very easy. So the first type of mirrors here, the one we are more commonly used to, are plane mirrors. So a plane mirror is just like your bathroom mirror. They are usually plane, so I guess yours too is plane. So imagine you have the mirror and you have the axis. Suppose you have an object here. Let's say this is you. You're the object, right? Okay, you are not a stick, but you understand. So if you are the object and yeah, your image, of course, formed by a plane mirror as viewed by any observer, I'm not very good at drawing, is going to be formed. So light rays live here, they are reflected into your eyes, but they appear to come from a position behind the mirror. Okay, my rays are not perfect. Actually, I needed to magnify a little. It needed to be something like this and something like that. Okay, a bit rough now, but not very important. So you get the point. You have an object that's somewhere here, and the image formed by a plane mirror is on the other side of the lens. The image is virtual, which means it cannot be formed on a screen. It's erect. It's the same size as the object. It's also the same distance, which means this distance is equal to this distance. So same distance to the mirror on the other side, and is laterally inverted. A layman way of saying it is that your right hand becomes your left hand. So those are the properties of images formed by plane mirrors, really the simplest types. Then we can move to the next type of mirrors, which are concave mirrors. So a concave mirror is a curved mirror. Say you have this is your mirror. It is just like a cave. No, it curves inwards. The reflecting surface is the inner surface. So there are a few important points to note as far as curved mirrors in general are concerned. The first important point to note is the focal point. Just like for lenses, it is the point where all rays converge to or are reflected by the lens, which means if you have parallel rays that come like this, they're going to be reflected to this point. Like that, and like that. So that's the focal point. The next important thing to note here is the principal axis. You know, it's this line over here that contains, it's an imaginary line if you want, that contains the object. If you suppose you have an object here, the focal point, and the pole, so the center of the mirror. That line is known as the principal axis. Then you also have another point known as the center of curvature. So you can tell yourself that this mirror, a curved mirror, is just a portion. It's just a portion of a sphere. So imagine you wanted to really like get back the sphere from which this portion has been cut. You would need a center. That center is the center of curvature, which means that if you take a compass, you know, you can really trace this circular path, and this is going to be the center of that circle. So that's the center of curvature. And in general, the focal length is just half of the radius of curvature. So it's half of this distance. We can show that mathematically and geometrically, that F is R over 2. So that being said, how do we know? How do we determine the image formed by a concave mirror? The first thing you need to take into account, just like I showed you in the previous case for convex lenses, is the reference point. The reference point for a concave mirror is this center of curvature, which means I'm just going to be doing sketches. They're not going to be very perfect, but I will try to add images on the screen somewhere here so that you can be following up with the exact geometrical diagrams, what is actually going on. So suppose you have so you have your concave mirror. Here you have your center of curvature. So this is the reference point. Why do I call it the reference point? Because if you place an object here, the focal length is always in between. If you place an object at the center of curvature of a concave mirror, then your image is going to be formed at the exact same position, but inverted. Hope you can see that. Which means image, so object, image. The image is inverted, as you can see. It's real. It's the same size as the object and also the same distance to the lens as the object is. So this is really your reference point. It's like a one-to-one conjugation, if you want. Image and object are of the same size and the same distance to the lens, to the mirror. Sorry. Then from here, tell yourself that, okay, if this is my reference point, if I move towards the mirror, then what's going to happen? If I move towards the mirror, then if I move the object towards the mirror, then what happens is that this image is going to shift on the other side because it's a reflection. So it's going to get larger and further away from the lens, from the mirror. Sorry, I keep saying lens, but it's a mirror. And if you take your object and you move away from the mirror, then the image is going to move towards the mirror and become smaller. So hope you can see the trick. Object gets closer, image gets further further away and larger. If object gets further, image gets towards the mirror and smaller. So that's really the trick you should use, which means if you take another configuration where we are having still our center of curvature is here. Here you have the focal length. Let's say we move the object a bit further away. So object is here. So it's beyond the center of curvature. Then we should expect our image to be formed closer to the lens and smaller than the object is. So it's going to be something smaller and closer to the lens. So that's the trick. If you take another situation where, oops, my drawings are really not good. So let's say here we have our center of curvature, focal length. If we move the object, let's say towards the mirror here, you see that we have moved from the center of curvature towards the mirror. Then the image is going to be formed further, and it's going to be larger. So it's going to be something like this. So that's really the simple trick that you can use to derive the image formed by a concave mirror. And then there are other two special cases that we can have here, which is if the image is at the focal point. So let's say here is F and here is C. So if the object is at the focal point, just like for the case we had with a convex lens, then the image is going to be formed at infinity. In other words, the rays would be parallel. They will hit the mirror, and they're going to be reflected really parallel to, reflect parallel to each other. So this is the case where the lens is at the focal point. And the last case is when we are between the focal point and the lens. So if the object is placed here, then in that case, the image is no more inverted and real, but rather it becomes virtual, magnified, and formed on the other side of the lens, like that. So in this case, it's virtual, magnified. Okay, so these are really the 5 cases you can have for a concave mirror. So let me recap. Your reference point is the center of curvature. If the object is placed at this position, the image is going to be formed at this same position, but it's going to be inverted. It's going to be of the same size as the object and the same distance to the lens as the object is. It's also going to be real and inverted. So that's your reference point. Then if you move your object further away, the image gets closer and becomes smaller. If you move your object closer to the lens, the image gets further and larger and bigger. And then the 2 special cases is when your object is placed at the focal point. In this case, the image is formed at infinity as the rays are parallel, as the reflected rays are parallel. Then if you place your object between the focal point and the lens, then the image is going to be virtual on the other side of the lens and magnified. So that's really what you can use. Then if we move to convex mirrors, the other cases, let me change sheet of paper. So with convex mirrors, things really get easier because there's just one configuration that can happen. The image formed by a convex mirror is always of the same type. So let's say we have this, we have our convex mirror. The reflecting surface is outside, so here. So the rays come parallel to the mirror and they are reflected this way, but they appear to come from a position on the other side of the lens. So you can already imagine that the image formed by a convex mirror is going to be virtual, as it appears to come from a certain position where there is really nothing. And that's really the sense of having a virtual image. So using ray diagrams and geometrical construction rules, we can show, I won't do it here, but you will always have at the screen an image with the exact geometrical drawings in order for you to follow up what I'm saying, because my drawings are not very good. So again, we have our focal point here. We have the center of curvature here, C. Let's say we place our object at any position at the center of curvature, for example. Then the image, we can show that the image formed by a convex mirror is going to be on the other side of the lens and diminished. So this is the image and this is the object. Hope you can see that. So this is the only configuration that you would have for a convex mirror. So image is virtual, it's erect, it's diminished, and it's on the other side of the mirror. Okay, so yeah, convex mirrors are really like much more easier than concave mirrors. An application of this is really in cars, like in car mirrors. Usually the mirrors you find are convex because they can capture a much wider field of view. Also, you can find convex mirrors on streets, on blind bands, where the cars that are coming towards an intersection do not see each other. We usually place a convex mirror at the corner in order that they can help the driver see the other portion of the field due to these properties. So hope you find this useful. If so, do not forget to drop me a like, subscribe, and drop a comment. If you have any suggestions, feel free to add them in the comment section. And I see you soon to talk about another interesting topic. And remember that physics is the belief that a simple and consistent description of nature is possible, like what you can see here.